Number theory, lecture 11, congruences. So we take a modulus, which is a positive integer, an integer m at least one, and we say A is congruent to B mod m if m divides A minus B. And congruence mod m is what is called an equivalence relation. So this relation, A is related to B if A is congruent to B mod m. It's reflexive. Every number is congruent to itself. It's symmetric. If A is congruent to B, then B is congruent to A. And it's transitive. If A is congruent to B and B is congruent to C, then A is congruent to C. And the equivalence classes are called congruence classes. So the congruence class of a number A modulo m is the set of all integers, x and z, such that A is congruent to x mod m. Sorry, x in z. So A is congruent to x mod m. And the set of congruence classes is denoted z mod mz. And this set is a finite set. We denote this congruence class by A plus mz. This is all the integers which are congruent to A mod m. It's a finite set. And in fact, it can be written as just the set of congruence classes for only those A's between 0 and m minus 1. Z mod mz consists of the multiples of m, the congruence class of 0, 1 plus mz, 2 plus mz, up to m minus 1 plus mz. Right? So this is all review. This is what we talked about at some length last week. And again, just to make sure, for example, if I take m equal to 7, there's the congruence class of 3 mod 7, which is exactly the same as the congruence class of 10 mod 7, because 3 is congruent to 10 mod 7. And the set of all congruence classes mod 7 has 6 elements. The multiples of 7, the congruence class of 1, this is all integers that leave a remainder of 1 when divided by 7, 2 plus 7z, all the way up to 6 plus 7z. Right? This is z mod mz is a ring. That means you can add and multiply congruence classes. If you have the congruence class A plus mz and the congruence class B plus mz, we can define the sum of these to be the congruence class of A plus B plus mz. So 3 plus 7z plus 6 plus 7z is 9 plus 7z, but 9 is congruent to 2 mod 7. This is 2 plus 7z. And similarly, you can multiply congruence classes. A plus mz, B plus mz is A times B plus mz. And again, we saw that this is well defined, and if you multiply the congruence class 3 mod 7 times the congruence class 6 mod 7, 3 times 6 is 18. But what is the remainder of 18 when you divide by 7? It's 4. So this is the congruence class of 4 plus 7z. Okay. And the identity, the multiplicative identity, is the congruence class 1 plus 7, 1 plus mz. Because if you multiply that by any congruence class a plus mz, you get 1 times a, or a plus mz. This is the multiplicative identity. The additive identity is just the congruence class of 0, which we just write as mz, the multiples of m. Okay. Any questions about this? Okay. So we like to solve equations in number theory. The simplest equation is a linear equation. And when we're talking about congruences, it's called a linear congruence. So in the text, this is section 2.2. Linear congruences. And this is theorem 2.2, which says the following, that m, a, and b be integers. M is the modulus, it's at least 1. A and b can be any integers, positive, negative, or 0. Let D be the greatest common divisor of A and M. Now we want to know, when can we solve the congruence AX congruent to B mod M? Let me just give an example. Suppose we want to solve the congruence 3x congruent to 5 mod 7. We want to find a solution. We want to find an integer solution to this congruence. So let's see. X equals 0 doesn't work. X equal 1 doesn't work. X equal 2 doesn't work. 3 doesn't work. 4 does work. Suppose we let x equal 4. 3 times 4 is 12. And 12 is congruent to 5 mod 7. So this linear congruence, it's like a linear equation, ax equal b, except it's a congruence, ax congruent to b mod m, has a solution, x equal 4, and in fact, any x congruent to 4 mod 7 is a solution. So just to make sure you understand what it means to solve a congruence, here's another example. Suppose we want to solve the congruence 2x congruent to 3 mod 7. What's the solution of this congruence? You want to find an integer that solves that congruence. So let's pause for a minute and I'll give you a chance to do this. Again, just plug in all the numbers, 0, 1, 2, 3, 4, 5, 6.
How about 5?
Sorry?
5.
Excellent. So suppose we let x equal 5. 2 times 5 is 10, and 10 is congruent to 3 mod 7. And you can take any number that's congruent to 5 mod 7. For example, 12. Does that x equal 12? 3 times 12 is 36. 36, let's see, sorry, 2 times 12. 2 times 12 is 24. 24 is congruent to 3 mod 7 because 24 minus 3 is 21, and 21 is divisible by 7. Okay? So that works. Right? Any question about these examples? It's important to understand the examples in order to understand the theorem. Right? We're solving a linear congruence. You have a modulus m, integers a and b, and we want to solve ax congruent to b mod m. Now, some equations don't have a solution. And maybe I'll do another example that maybe doesn't have a solution. Suppose I want to solve 3x congruent to 5 mod 6. So you can try all the numbers, 0, 1, 2, 3, 4, 5. There's no solution. And why is there no solution? If there were a solution, if x were a solution of this equation, then 3x minus 5 would be divisible by 6. That is, would be equal to 6 times y. Or if I rearrange this, 3x minus 6y would equal 5. If I factor a 3 from the left-hand side, 3 times x minus 2y equals 5. But 3 doesn't divide 5. This is impossible. So this congruence has no solution. There's no integer x such that 3x is congruent to 5 mod 6. So again, all this is stuff you have to think about. This is not mathematics that you can understand the instant you see it. So let's go back to the theorem. Let D be the greatest common divisor of A and M. A is the coefficient of x, M is the modulus, D is their greatest common divisor. The congruence AX congruent to B mod M has a solution. Right? It doesn't always have a solution. If and only if B is congruent to 0 mod D. So if and only if D divides B, where D is the greatest common divisor of A and M. Right? So what is the proof? So the solution, AX congruent to B mod M, has a solution or is solvable if and only if there exists a Y such that AX minus BY is equal to M. Sorry, there exists a Y such that AX minus B is divisible by M, so AX minus B equals MY. Or if and only if, I just rearrange this equation, AX minus MY equals B. And this linear equation has a solution if and only if B is congruent to 0 modulo the greatest common divisor of A and M, which is D. So that's the proof of this theorem. It's actually the first part of a theorem. But, the congruence, AX congruent to B mod M, is a solution if and only if this is satisfied. Now, let's look at these two cases. Here, in this case, this is A, this is M, and the greatest common divisor of 3 and M, of A and M, or 3 and 7, is 1, and 5 is certainly divisible by 1. In this instance, my A was 3, my M was 6. The greatest common divisor of 3 and 6 is 3, and 3 doesn't divide 5. 3 does not divide 5. So there's no solution to this congruence. Okay. Right. And the second part of theorem 2.2 tells us when there is a solution, how many solutions are there? So just note, if AX is congruent to B mod M, and X prime is any number congruent to X mod M, then I can multiply a congruence by a number. AX prime is congruent to AX, but AX is congruent to B mod M. So if X is a solution and X prime is congruent mod M to X, X prime is also a solution. So if there's one solution, there are infinitely many integers that are solutions. So the interesting question is, how many solutions are there, no two of which are congruent to each other? And the second part of theorem 2.2 says, so we're looking at this congruence, always. This is the linear congruence. AX congruent to B mod M. If B is divisible by M, if B is congruent to 0, divisible by D, mod D, then this congruence has exactly D pairwise incongruent solutions. In particular, if the greatest common divisor of A and M is 1, if D equals 1, then the congruence has a unique solution modulo M. So how do we prove this? If X1 and X are solutions, then AX1 is congruent to AX, because they're both congruent to B mod M, which means the difference, AX1 minus AX, which is A times X1 minus X, is divisible by M, is congruent to 0 mod M. So this difference, A times X1 minus X, is a multiple of M, is say M times Z, for some integer Z. And remember, we let D be the greatest common divisor of A and M. So D divides A and divides M. If I divide this equation by D, A over D is an integer and M over D is an integer. And if D is the greatest common divisor of A and M, then the greatest common divisor of A over D and M over D is 1. So the integer M over D divides X1 minus X times this, but M over D is relatively prime to A over D. So by Euclid's lemma, x1 is divisible by m over d. x1 is congruent to x modulo m over d. And every integer, and any integer congruent to x mod m over d is a solution. So what does it mean to say x1 is congruent to x mod m over d? x1 is equal to x plus I times m over d for some I. And if you let I run from 0 up to d minus 1, these are all solutions of the congruence, and they're different modulo m. No two of them are congruent modulo m. Let me just sort of explain that in maybe a little bit more detail. And first, I'll start again with an example. Suppose I want to solve, let's take an example, 6x congruent to 9 mod 15. I want to solve this congruence. So in terms of the standard form ax congruent to b mod m, my a is 6, my b is 9, my m is 15, my d, which is the greatest common divisor of a and m, that's the greatest common divisor of 6 and 15, that's equal to 3, right? 3 is the largest number that divides 6 and 15. And b, what is 9? B, which is 9, is congruent to 0 modulo 3, which is d, right? So b is congruent to 0 mod 3. So this equation has a solution, and I claim it has exactly 3 incongruent solutions. What is one solution of this congruence? Let's see. Solve 6x congruent to 9 mod 15. So try 0. I'll just do it by 1, 2, 3, 4. Suppose I take x equal to 4. 6 times 4 is 24. 24 minus 9 is 15. So any x congruent to 4 mod 15 is a solution. So in fact, we can say the following. So 6 times 4 so x is congruent to 4. Suppose, let me do it better. Let x1 be another solution. Then 6 times x1 is also congruent to 9 mod 15. So I have 6x congruent to 9 mod 15, 6x1 congruent to 9 mod 15. So 6 times x1 minus x, the difference, that's 6x1 minus 6x, is congruent to 9 minus 9, is congruent to 0 mod 15. So 6 times x1 minus x is divisible by 15, is 15 times some number z. If I divide by 3, I get 2x1 minus x is equal to 5z. 5 divides 2 times x1 minus x, but 5 and 2 are relatively prime. The greatest common divisor of 2 and 5 is 1, so that means 5 divides x1 minus x, where x1 is congruent to x, mod 5. And if x1 is any number congruent to x mod 5, we get a solution. If x1 is congruent to x mod 5, it solves this equation, it solves this equation. We have a solution. So what numbers are congruent to x mod 5? X plus 5, x plus 10 are all congruent to x mod 5. So if x equals 4 is one solution, I get 4 plus 5, 4 plus 10, 14. These are different congruence classes, mod 15. And each of these is also a solution. Let's just check. 6 times 9 minus 15 is 54 minus 15 is 39. It's 39. Oh, sorry. That's not what I mean. That's a true statement, but it's not what I wanted to show. So I claim all three of these numbers, 4, 9, and 14, are solutions of my congruence. The congruence was 6x congruent to 9 mod 15. We already saw x equal 4 as a solution. What about x equal 9? 6 times 9 minus 9 is 54 minus 9 is 45 is 3 times 15. So 9 is the solution. What about 14? 6 times 14 minus 9. What's 6 times 14? 6 fours are 24. It's 84 minus 9.
75.
84 minus 9 is 75. 75 is 5 times 15 is the solution. So these are all solutions. They're exactly three pairwise incongruent solutions modulo 15.
Mm.
That's what the theorem says.
Can I write that?
Sure.
Okay, I'm done.
Just 1 second, please. Okay, so here's the congruence. What are all the solutions? Can someone give me one solution?
5.
Well, suppose you take x equal to 5. So 6 times 5 is 30. 30 minus 8
22.
22. Is that divisible by 14?
X equals 6.
Right, so this guy doesn't work, right? Because
Oh,
not congruent to 0 mod 14. X equals 6. Let's try that. 6 times 6 is 36. 36 minus 8 is 28, is 2 times 14. So this is congruent to 0 mod 14. So one solution is x equal to 6, or more generally, any number that's congruent to 6 mod 14. So for example, 20 is congruent to 6 mod 14. So 20 should also be a solution. Let's see, 6 times 20 minus 8 is 120 minus 8 is 112. Let's see, is that a multiple of 14? If I take 14 times 8, that is 112. So this is congruent to 0 mod 14. Of course, it has to be. I mean, any number congruent to 6 mod 14 is a solution, like 20. Well, but what about another solution? Supposed to be another solution, x1, which is not congruent to 6 mod 14, right? Can we find another solution? So the theory says you can take, so in this case, for this congruence, A is 6, B is 8, the modulus is 14, D, which is the greatest common divisor of A and M, that's the greatest common divisor of 6 and 14. What's the greatest common divisor of 6 and 14? What's the largest integer that divides both 6 and 14?
Two.
2. So the general theory says we can take x1 to be any solution x plus I m over d, where I runs from 0 to d minus 1. I is either 0 or 1. What is this? X, one solution we found was 6, plus I times, what is m over d? M is 14, d is 2. 6 plus I times 7. So we get either 6 if we choose I equal to 0, or 13 if we choose I equal 1. So 13 should be another solution. Let's check. 6 times 13 minus 8. 6 times 13,
78.
78, minus 8 is 70. Is 70 divisible by 14?
Yeah.
Yes. 14 times 5.
14 times 5. So 13 is the other solution. So all solutions of the congruence 6x congruent to 8 mod 14, any x congruent to 6 or 13 mod 14.
Wait, how about 20? Why you didn't include 20?
But 20 is congruent to 6. These are the congruence classes of solutions. These are all solutions, any number congruent to 6 or 13 mod 15.
Not 14.
Right? 14 is the modulus. By the way, what's another number congruent to 13 mod 14? Minus 1.
Yeah.
Minus 1 is congruent to 13 mod 14, because the difference is 14. And in fact, if I let x equal to minus 1, 6 times minus 1 plus 8, 6 times minus 1 is congruent to 8 mod 14, because minus 6 minus 8 is minus 14. So that's just another way to write the solution. But so either any x congruent to 6 or 13, which is the same as saying any x congruent to 6 or minus 1 mod 14 is the solution. So there are infinitely many different integers that are solutions, but they all fall into exactly 2 congruence classes. Okay. So again, the most important part of this proof is that AX congruent to B mod M is solvable if and only if B is congruent to 0 modulo the greatest common divisor of A and M. And if this condition holds, the number of solutions modulo M is is D. Is D. Suppose the modulus M is chosen to be a prime number P. So we want to solve a congruence AX congruent to B mod P. So this is solvable if and only if B is congruent to 0 modulo the greatest common divisor of A and P. Now, P is a prime. What are the numbers that divide a prime? Only itself in 1. So if A is not divisible by P, if A is not congruent to 0 mod P, then the greatest common divisor of A and P must be 1. Right? If P doesn't divide A, the greatest common divisor of A and P is 1, and AX congruent to B mod P has a unique solution mod P. Right? In particular, AX congruent to 1 mod P has a unique solution. So if I take, for example, P equal to 7, 2x congruent to 1 mod 7, the greatest common divisor of 2 and 7 is 1, and the solution is, there's only one solution mod 7. X equal 4 is the solution because 8 minus 1 is divisible by 7. X congruent to 4 mod 7. If I take 3x congruent to 1 mod 7, 3 and 7 are relatively prime. The greatest common divisor is 1. This has a unique solution. What is the solution? I think 5 is the solution, because 15 minus 1 is 14. What about 6x congruent to 1 mod 7? 6 and 7 are relatively prime, so this will have a unique solution. What is the unique solution mod 7 of this congruence? What's the solution of that congruence?
Is it 8?
Sorry? Was this,
Is
I
it
just didn't hear
8?
what you said.
I said, is it 8?
So 6 times 8 is 48.
Linguistica.
48 minus 1 is 47, and 47 is not divisible by 7. So 8 doesn't work.
Then it's 6.
6. 6 times 6 is 36. Take away 1 is 35, which is 5 times 7. So any x congruent to 6 mod 7 does work. Right? And mod 7, these are the unique solutions of this. So certainly you need to be able to learn how to solve by hand these relatively simple linear congruences. Okay. All right. Now, integers, the congruence classes modulo of prime are particularly important and nice. So let me just review some definitions. So we say that G is an additive abelian group. So there's a binary operation which we're running as addition if addition in this is associative. So x plus y plus z is x plus y plus z. It's abelian or commutative. X plus y equals y plus x. There's an identity element, which we can call 0. 0 plus x is equal to x for all x. And there's an additive inverse. For all x in the group, there is a y in the group with x plus y equals 0. So for example, if we take G to be the integers, or the real numbers, or the rational numbers under addition, these are all additive abelian groups. Okay, that's the definition. Now, R is a ring if R has two operations, addition and multiplication. And with respect to addition, R is an additive abelian group, but multiplication satisfies two properties, three properties actually. It's associative. X times y times z is x times y z. It's commutative. Xy always equals yx. And there's a multiplicative identity. 1 times x equals x for all x. Right? And there's also a distribution law, which says x times y plus z is xy plus xz. So examples of this, of rings are, again, we could take the integers, the real numbers or the rational numbers with the usual operations of addition and multiplication. So these are rings, and the important one we saw in this chapter is the ring of congruence classes mod m for every m. Now, so suppose R is a ring. We say X, an element of the ring, is invertible, has an inverse, if there exists, this means exists, a Y in the ring with X times Y equals 1. right? So, for example, in the integer z, 2 is not invertible because there's no integer x or y such that 2 times y is 1. So in z, 2 is not invertible. In the rationals, 2 is invertible. Take y equal to a half. 2 times a half is 1. So whether an element is invertible or not depends on what ring you're looking at it in, right? But the integers contain elements that are not invertible. The rationals, if you take any non-zero number, a over b, in Q, if a over b is not 0, then b over a is another non-zero fraction, rational, and the product is 1. So in Q, every non-zero element has an inverse. That's not true in the integers, okay? So to say an element in a ring is invertible means there's something you can multiply it by to get 1. And suppose we take, for example, r to be the integers mod 4. So if we take x equal to the congruence class 2 plus 4z, this is not invertible because you just take 2 plus 4z and multiply it by everything possible. You have 0 plus 4z, 1 plus 4z, 2 plus 4z, 3 plus 4z. So if you multiply this by 2 plus 4z, you just get 0 plus 4z, or 4z. If you multiply 1 plus 4z by 2 plus 4z, you get 2 plus 4z. It's not 1. It's not 1 plus 4z, which is the unit. 2 plus 4z times 2 plus 4z is 4 plus 4z, which is the same as 0 plus 4z. Again, that's different from the congruence class of 1. And 3 plus 4z times 2 plus 4z, 3 times 2 is 6. 6 is the same as 2 mod 4z. Again, that's not 1 plus 4z. So 2 plus 4z is not invertible in z mod 4z, right? It's not invertible. And so rings where every non-zero, 0 is never invertible. 0 times anything is always 0. It's not equal to 1. But a ring where every non-zero element has an inverse, those are very nice. They're called fields. So a field, this is the word we're defining, is a ring in which every non-zero element is invertible. And invertible elements are called units. So a ring where every non-zero element is invertible, that's what a field is. So Z is not a field. The rationals, the reals, even the complex numbers are fields. Okay, that's the definition of a field. And the integers mod 4 do not form a field But this is a very important theorem. If P is a prime number, the integers mod P do form a field. Right? So this is the same as saying if you're looking at congruence classes mod P, you can not only add, subtract, and multiply, you can also divide. So proof. So must prove that if A plus PZ is a congruence class different from the zero class, then there exists a congruence class X plus PZ such that if I take X plus PZ times X plus PZ, this is the congruence class of 1. The product of these two is 1. What is 1 in the integers mod P? It's the congruence class of 1. This is the multiplicative unit. Right? But of course, if I multiply A plus PX and X plus PX, this is the congruence class AX plus PZ. Right? This is the product of these two congruence classes, A mod P and X mod P, is AX mod P. So there's an X such that this congruence holds if and only if there exists X with AX congruent to 1 mod P. And to say that A plus PZ is not the zero class means that the greatest common means that A is not divisible by P. So that means that A is not congruent to 0 mod P. P doesn't divide A. So the greatest common divisor of A and P is 1, which means that AX congruent to 1 mod P does have a unique, has a solution, and it's a unique solution modulo P. So, for example, suppose I take P equal to 5. I want to solve 7x congruent to 1 mod 5. Of course, that's the same, 7 is the same as 2. That's the same as 2x congruent to 1 mod 5. And you can see that one solution of that, 2 times 3 is 6, is congruent to 1 mod 5. So if I take any x congruent to 3 mod 5, the congruence class of 7 plus 5z times the congruence class of 3 plus 5z is the congruence class of 21 plus 5z, and 21 is congruent to 1 mod 5. In fact, Z mod 5z is a field by the theorem because P is prime. P equal 5 is a prime number. So Z mod 5z is a field. So suppose we want to compute the inverses, that's what we call the element, the inverses of the non-zero congruence classes mod 5. What are the non-zero congruence classes mod 5? 1 plus 5z, 2 plus 5z, 3 plus 5z, and 4 plus 5z. So we have to be able to multiply this by something to get 1 plus 5z. Each of them. Something. So what's the inverse of 1? Well, 1 times 1 is 1. So 1 plus 5z times 1 plus 5z is 1 plus 5z. What's the inverse of 2 mod 5? It's 3. 2 plus 5z times 3 plus 5z is 6, which is the same as 1 plus 5z. 3 plus 5, 2 times 3 is 1, 3 times 2 is 1. 3 plus 5z times 2 plus 5z is 1 plus 5z. And what's the inverse of 4? Well, 4. Well, 4 times 4 is 16. 16 take away 1 is 15. So 4 plus 5z plus 4 plus 5z is 1 plus 5z.
Okay, Professor,
Yes.
I don't understand how 2 plus 5z, why is it times 3 plus 5z?
Excuse me?
I don't get the second one, 2 plus 5z times 3 plus 5z. Why is it 3?
Well, 2 times 3 is 6. Okay?
Yeah.
6 is congruent to 1 mod 5.
Okay,
So 2 plus 5z times 3 plus 5z, that's 2 times 3 plus 5z, which is 6 plus 5z, which is 1 plus 5z. 6 is congruent to 1, so these two congruence classes are the same.
okay.
All right, well, let's do one final exercise. Compute the inverses of the 6 non-zero congruence classes modulo 7, right? Z mod 7z is a field, so every non-zero element has an inverse. So take a minute or 2 or 3 and calculate the inverses. So you're going to make a table. 1 plus 7z, 2 plus 7z, 3 plus 7z, 4 plus 7z, 5 plus 7z, 6 plus 7z. So here we have the class. These are the 6 non-zero congruence classes. And what is the inverse? Right? I mean, of course, the inverse of 1 is always 1. 1 times 1 is 1. Right? So you have to figure out the 5 remaining non-zero congruence classes. See, also, we should be having a midterm at some point, and I said I would give 2 weeks' notice, so let's say that the midterm is 2 weeks from today. Wednesday, October 25th, on campus. Right. So what do you multiply 2 by to get 1 mod 7?
How about 4?
4, yeah. 2 times 4 is 8. 8 minus 1 is 7. And of course, once you have one inverse, you have another, because if 2 times 4 is congruent to 1 mod 7, 4 times 2 is congruent to 1 mod 7. So when you have one, you have another. What's the inverse of 3 mod 7?
Three times 2?
Well, 3 times 2 is 6. 6 is not congruent to 1 mod 7. 6 is congruent to, because 6 minus 1 is 5. It's not divisible by 7.
Is it congruent to itself?
Yeah, 3. Because 3 times 3 is 9. Oops, sorry, that's wrong. I don't know why I said that. No, 3 times 3 is 9, and 9 is minus 1 is 8. Huh. What's the inverse of 3 mod 7? What do you multiply 3 by to get something congruent to 1 mod 7? Just start looking at all the multiples of 3, subtract 1, until you find one divisible by 7. What are the multiples of 3? 3, 6, 9, 12, 15.
7?
Sorry, what?
7?
Oh, so I didn't hear, excuse me?
3 times 7 is
Well, 3 times 7 is 21. Take
divided
away
by
1, you
4.
get 20. That's not divisible by 7.
Sorry, I was doing 21 divided by 7.
What's 3 minus 1?
2?
Is that divisible by 7? Well, I don't think so, right?
No.
2 is not divisible by 7, but what multiple of 3 minus 1 is divisible by 7? See, 6. 6 minus 1 is 5. That doesn't work. 9. 9 minus 1 is 8. That doesn't work. 12 minus 1 is 11. That doesn't work. 15 minus 1 is 14. That does work, right? 14 is 2 times 7. So the inverse of 3 is 5. 3 times 5 is 15. 15 minus 1 is divisible by 7. And a 3 times 15 is congruent to 1 mod 7. Then 5 times 3 is congruent to 1 mod 7. What about the inverse of 6? What's the inverse of 6 mod 7? What multiple of 6 minus 1 is divisible by 7? Where 6 is the same as minus 1 mod 7. Minus 1 times minus 1 is plus 1. So 6 plus 7z should be its own inverse. Because 6 times 6 is 36. Take away 1 is 35 is divisible by 7. So these are the inverses.
Is
of the
that 6
non-zero
plus
congruence
6z?
classes mod 7. What?
Is that 6 plus 6z?
No, 7. Sorry.
Okay.
These are all congruence classes mod 7. So everything we talked about today is really fundamental in number theory, and in the midterm 2 weeks from today, this will certainly be on it. I mean, you have to know how to solve a linear congruence, and you have to know why the integers modulo a prime number p form a field, and how to find the inverse of an element in the field. This is basic arithmetic. Okay, well. So this
When are we
is,
gonna have a review for the midterm?
oh yeah, there's definitely a review and multiple review sessions on Zoom.
Okay. The midterm is there's gonna be many.
Have you
2
set a
weeks from
date for
today.
that?
I mean, how many questions will be on the midterm?
I don't know, 6 or 7.
Have you set a date for the midterm?
Yeah, it's right here. Wednesday, October 25th. 2 weeks from today. I've been saying that over and over. 2 weeks from today.
And the review is posted, right?
It will be.
Oh, will be okay.
Okay. All right. Any questions before we end for the day? Okay.
No,
Bye,
thank you.
all.